Okay, so in this chapter, we're going to dive a little bit deeper, and I do mean that literally. We're going to start to think carefully about what's going on in the center of the sun and how we can use that information to better understand stars in general. Okay, and so we're giving away, the what we're going to find a little bit here with the title, "The Sun, a Nuclear Powerhouse." So you'll see what I mean very shortly. So, okay. Um, we've long recognized as a species that the sun is the source of energy for basically almost all life on Earth and things like weather or energy production that we might want to perform. And so, for this reason, many, if not most cultures at some point or another deified the sun and basically considered its energy to have a divine source, something that wasn't like what we find on Earth. And that was pretty standard view until about the 1800s, where astronomers and other scientists started to try to think, okay, where is the sun's energy coming from, right? Newton told us how objects orbit the sun and they follow the same law of gravity as things down here on Earth. So why not imagine a sun that's made of things like what we find on Earth? And so one thing that we see that emits a lot of energy on Earth is a fire, right? Whether that's from wood or from coal or from something like a gas like propane. And so people initially proposed that the sun's energy was coming from something like a fire. And to be honest, I think a lot of people who haven't taken an astronomy course might still think of the sun as a big ball of fire somehow. That's not quite right. And we're going to talk about how the sun is a little bit different. The main problem with this is that it would basically run out of energy really quickly. And so this isn't a viable method to produce energy for long enough. We would also see different spectral lines than what we see. So when we look at the sun, we mostly see spectral lines from hydrogen and helium. And hydrogen burns okay, but it would need some oxygen to do that. And helium doesn't really react at all. So we need to think about some other possibilities. So when we're dealing with energy, the reason we talk about it at all is because it's something which is a conserved quantity. And so what do we mean by that? Well, we can look at this pendulum here as an example. If we take a pendulum and we lift it up, what we're doing is we're storing energy between the pendulum and the Earth in the gravitational field. We call that potential energy. When we let it go, it's going to swing downward. It's losing that gravitational energy, but it's gaining motion. It's gaining what we call kinetic energy. And then it can basically go the other way. So as it goes back upward on the opposite side, it's turning that kinetic energy into potential energy again. And so this is true of all types of energy, that basically we can transform them, but we cannot create or destroy them. We're going to talk about something that complicates that a little bit, but really doesn't change things too much in a few slides. But you can imagine that one option that you might have here is that we could convert gravitational energy or kinetic energy into heat somehow. And maybe that's where the sun's heat and therefore light comes from. Right, because we know if we can get it hot enough that it'll start to emit light, it'll become a black body. And so some scientists in the 1800s proposed that maybe meteors falling into the sun was the source of this energy. So we have kinetic energy turning into heat. And in order for that to happen, we would need about an Earth's mass worth of meteors to fall in every year. And we can use Kepler's third law, which tells us how the radius and period are related. It turns out that depends on the sun's mass. So if the sun's mass was changing that much, we would see the Earth's year, Earth's orbit change by about 2 seconds every year. We don't observe that, so we can rule out the meteor hypothesis, which sounds a little ridiculous as well, but sometimes the world works in funny ways. Okay, so a third option was first proposed by Kelvin and Helmholtz, which is a lot more sensible. This is actually how Jupiter gets its energy, which is okay. We have a ball of gas. what if it's just still slowly falling inward, settling, differentiating even maybe? Uh, so as it contracts, it's taking gravitational energy and it's turning it into heat. Maybe that's what's the source of the sun's energy. So for that to happen, Helmholtz and Kelvin did the math, and you would only need the sun to contract by about 40 meters per year. Not very noticeable. So this is actually somewhat viable. We wouldn't really easily see it. However, if you do the math some more, they could already at that time measure the radius of the sun. And so what they found was that this could only last for about 100 million years. It can't generate energy for very long. However, geology and those chondrite meteorites tell us that we need the sun to have been around for at least 4.5 billion years, emitting some energy. So because of this, we cannot rely on gravitational collapse alone, although it does play an important role. So it's relevant, but not the sole source of the energy of the sun. However, for something like Jupiter or Saturn, this is where its internal energy comes from, is just from gravitational collapse. Okay, so in order to solve this puzzle, we needed someone who was really smart and working on something totally unrelated, which is often how science happens. So Einstein, you probably heard of him, he was trying to think about what happens if you were to ride a photon, if you were to travel at the speed of light, or looking at light. It turns out light, because it's going as fast as things can go in the universe, if you try to go faster and faster approaching the speed of light, you run into a bunch of problems. And so it was when he was going through trying to understand these problems that he was able to derive this famous equation, E equals mc squared. Now, I'm not going to give you the derivation of it, but it's basically what you have to have if you want energy and momentum to still work as you go faster and faster, like near the speed of light. And if you want those things to still be conserved, you need, when something is still, so E equals mc squared is actually only true when something is sitting still, but you need it to be the case that basically mass we can interpret as a concentrated form of energy. So the c squared here, the c is the speed of light. So c squared is just a really, really big number. So what that's telling you is that if I have a little bit of mass, I'm going to multiply it by a really big number, and that's going to give me some amount of energy. And that basically I can go back and forth. Now, Einstein thought this was just like a mathematical fiction, basically, not something that could actually happen, because back then they didn't know of any mechanism to allow you to do this. Like they were like, okay, maybe it's technically true, but if there's no way to go from matter to energy or vice versa, what does it matter? Okay. However, we're going to see very shortly that since that time, we have discovered many ways to go back and forth. So one way is shown here, where we have an electron and its antimatter partner, the positron. So these are just two particles, and if they happen to collide, then they convert into energy. They convert into gamma rays, which is just a type of energy, right? So they release a lot of heat and motion. And we can calculate it using E equals mc squared, and we get the right answer, which is really wonderful. So if we were going to understand how to actually do it, how to actually use E equals mc squared, we need to take a moment to understand what everything in the universe is made of. And here it is. We have a nice little chart. These are the elementary particles. By elementary, we mean these are the things that are as small as you can go. You can't break them apart anymore. And so what we find when we get down to these small particles is that they can actually do things that are really weird. We can, if we combine them in certain ways, it's almost like a chemical reaction. They can turn from one thing into another thing. But so in chemistry, you can have a reaction. You can turn, sodium and chlorine into sodium chloride. So you've changed things, but really, if you look under the hood, it's the same stuff inside. You have the same atoms. With elementary particles, that's not true. So you can actually take one of these things and transform it to where it disappears. It goes poof out of existence. and it turns completely in. It reappears as something else or a bunch of other things. And that sounds crazy, but there are still some rules. So one rule is that we have to conserve charge. So if I have a +1 charge like a proton, I can't just poof and it turns into a -1 charge like an electron. That's not allowed. I also have to conserve some other things. One of them is lepton number, so like electroniness. So if I have an electron, I can make it go away, but I have to get something else that's electrony, like this electron neutrino, to pop back out. So we have to be careful with these conserved quantities, and if you decide to become a physicist, you'll spend a lot of your time learning all about them and how to apply these rules. For this class, we're not going to be too worried about them. So one thing that I should mention is that we have all of the particles here, but we actually have a separate kind of mirrored version of all these particles, the antimatter version. So each of these things, like the electron, for example, has an antimatter particle, which is exactly the same, but it has the opposite charge. So an electron we know has a -1 charge. So its anti-electron partner, which we actually have a name for that one, the positron, is exactly like an electron, but it has a +1 charge. And if these two particles touch each other, then they just go poof and they go matter into energy. So that's one really cool way to go from matter to energy, is if you happen to have a particle and its anti-particle partner. Okay. Now, most of the universe is not the anti-particle partners because those all went poof very early on in our history. So pretty much they're all gone, except for a few stragglers and ones that are made by things like our sun. So our sun makes a little bit of antimatter. We're going to learn about that. So it's not like anything too crazy or exotic. It's just normal stuff, but with the opposite charge. But it has this nice property where if it touches its partner, they both go poof and turn into energy. So that's one way to go from matter to energy. We can also go from matter to energy when things decay. So I can have a heavy particle like this top quark, and it'll decay into a lighter particle, maybe like something like an up quark along with other stuff. And when it does that, it'll release a bunch of energy because the top quark has a heavier mass than the up quark. So as it decays, that extra mass that seems to have vanished gets turned into energy. So this isn't a violation of energy conservation. It's just what it's telling us is we should interpret mass as a type of energy, like how chemical energy is a type of energy. It's often locked away, but if we do the right process, right, if we take our block of wood and set it on fire, we can get the chemical energy to come out in the form of heat. And similarly, if we take our electron and we touch it to a positron, we can get the mass energy to come out as a form of heat. That's one way to do it, and we're going to see very shortly another way. Okay, so these are the fundamental particles. Just to give you a little bit more detail, if you're interested, I would encourage you to go and read about this. There are plenty of wonderful books I'm happy to recommend. But basically, these purple guys here, these are the quarks. Those make up the things like protons and neutrons. So inside of protons and neutrons are these guys, quarks. The green ones, those are the leptons. So these are all things either like the electron, but heavier, or like the neutrinos, which we're going to talk about very shortly as well. The red things, these are bosons, gauge bosons. Those are all associated with different forces of nature. So the photon is associated with the electric and magnetic forces of nature, and the other ones we're going to talk about shortly. And then finally is the Higgs. This is the weird guy. You can kind of see off by itself, scalar boson, and it's responsible basically for giving things mass. So not all the mass of things, but a lot of it comes from in interacting with this Higgs boson. So that's your brief overview of all particle physics. Okay, so moving on, we should talk about the atomic nucleus, and this will help us understand another way to convert mass into energy. Okay, so this is where we're headed. We want to understand, let's think about what we're doing. We want to understand where the sun's energy comes from, and I'm telling you it has something to do with E equals mc squared, but in order to use that to our advantage, we need a mechanism that lets us go from matter to energy. One mechanism is to have antimatter. That's not how the sun does it, though. And so, okay, let's learn about the other way to do it. Well, to see how that happens, we should spend a moment to understand what's happening in the nucleus. So remember, the nucleus, that's the center of your atom. It's really, really tiny. So an atom is already small, and a nucleus is about like 10,000 times or 100,000 times smaller. Okay, so nuclei are very small. They're made out of protons and neutrons, which remember, those are made out of quarks, but we don't need to worry about that right now. So the neutrons are neutral, and the protons have a positive charge. You may have learned before in school that if you have two positive charges, they want to push away from each other. They want to repel. So maybe you've wondered before, why is it that the nucleus has a bunch of things that hate each other inside? And it turns out that's because there's another force happening inside the nucleus. So if you remember, I said that all of these red boxes, these red particles here, are associated with forces of nature. So the photon, the light particle, is associated with electric and magnetic forces. The gluon, the one at the top, its name is kind of a joke because it glues things together. The gluon is associated with a new force that we only really see inside of a nucleus or smaller. So it's a new force. It only works in very small places over short distances, but it's incredibly strong. Okay, and so it's very creatively been named the strong nuclear force. It's a force that's very strong. It's able to hold those protons and neutrons together, even though the protons want to split apart. The strong nuclear force is dominant, so it holds it together, and that's how we're able to get nuclear stability. Now, if I put too many protons in a nucleus, then the strong nuclear force can't quite hold it anymore, so it wants to go flying. And this is actually why you need neutrons there, because the neutrons, they don't have a charge to them, but they do help make this glue, the strong nuclear force, stronger. So the neutrons are also emitting gluons and absorbing them, so they reinforce the structure. That's why heavier elements tend to have a lot more neutrons. So a light element, maybe every proton there's one neutron, whereas for a heavy element, maybe every proton there's two neutrons. It needs the extra help to stabilize. Okay, and I should mention there's also a weak nuclear force. That's what the W and Z bosons, the other two red boxes here, are doing. The weak nuclear force is important. It's basically what allows some particles to transform from one to another. So it gives you like some more possible reactions that can happen. And we'll see an example of that shortly. Okay, so before we get there though, we should take the final piece of the puzzle, which is this idea of binding energy. And so this is really tricky. It took physicists a long time to figure out, but basically some nuclei are happier than others, okay? And that has to do with the strong nuclear force. And so you might then wonder, well, what is the happiest nucleus? And you might naively guess that it's like a really small one, or maybe really, really naively guess that it's a really big one. It turns out it's neither. It's something right in the middle. It's iron. So iron is the happiest nucleus. And that's why it's at the top of this chart here. And basically everything lower down in this chart is less happy. So what do I mean by that? Well, the happier something is, the lower energy state it's in. Okay. So iron is in a low energy state. It's like a water bottle that you picked up and then you dropped it. When it's on the floor, that water bottle's in a low energy state. It's happy. It's where it wants to be. If you lift the water bottle up, then it wants to fall. The only thing keeping it from falling is your hand in the way. You move your hand, it's going to do what it wants to do. It's going to fall. So very similarly, all of the rest of these atoms, these nuclei, they want to be like iron, but there's something in the way, which is that they need a buddy to come help them. But if you get two atoms close to each other, they're going to repel because the electric force, the protons push against each other, that can reach out farther than the nuclear force can stick together. So they can only stick together or break apart once things are close. But if things are far, the electric force wins and you get things that basically things are unable to be happy. They're unable to go closer to iron. Now, what's weird is iron's kind of in the middle. So if you're a small element, what do you want to do? you want to glob on to other nuclei until you're bigger, 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 until you look like iron. But if you're a big nucleus, you're unhappy. What do? You want to do? You want to break apart, break apart, break apart until you're small like iron. So iron's in the middle here. Everything wants to go toward it. We use this idea of binding energy to talk about this. It's a little confusing. It's kind of opposite. So binding energy, you have a lot of binding energy when things are happy. So what does that mean? Well, when things are happy, you're technically in a low energy state overall. So the binding energy is kind of like how much lower your energy is than it would have been if these things were separate. Okay, so when they bind together, that's when you get the binding energy. But the binding energy is actually a reduction. Okay, so weird. How does this reduction manifest? Well, it manifests as mass difference. So if I weigh, so iron has 56 nucleons, protons and neutrons in it. So if I weigh out 56 nucleons separately, it turns out they weigh more than if I put them together as iron. Okay, so iron is lighter than the things that make it, which feels weird. So what happened there? Well, we had to have released some of that mass and converted it into energy somehow if we make iron out of smaller elements. Or similarly, if we have a big element and we break it apart, we've also released some energy somehow. Its mass per nucleon goes down. So that's what binding energy is measuring. So we want to give some names to these ideas. So when we put things together, that's fusion. So small atoms like hydrogen want to fuse together and turn into iron eventually. Bigger atoms like uranium undergo fission. They want to break apart. They want to sort of fission. They want to break apart, get smaller, and get closer to iron as well. Okay. So this is the big picture here. So instead of using antimatter to make mass go into energy, we can notice that atoms have this relationship where smaller ones want to go to the middle and bigger ones want to go to the middle. And so if we, just like a chemical reaction though, your block of wood usually doesn't just catch on fire by itself, even though it wants to be turned into soot. You have to light it. You have to give some activation energy. It's the same thing with nuclear reactions. We're going to have to give them a lot of energy so that those nuclei can bounce around and finally crash into each other and then undergo the nuclear reaction. Okay, so that's the hard part. But it's good that it's hard because otherwise we probably wouldn't be able to exist, right? There would be nuclear reactions happening all the time and they would destroy us. Okay, so here's a picture of a nuclear reaction. So we're going to take two hydrogen atoms, which are just protons at this point, just protons, and they're going to react together. One of those protons is going to turn into a neutron, and they're going to stick now and form a new type of hydrogen, a new isotope, which is called deuterium, or 2H. And in that process, in order to conserve all these quantities that we have to conserve, they're going to make a neutrino, which is a weird ghostly particle we're going to talk more about later. And they have to make a positron, right? They're making antimatter. The sun is making antimatter within it. It has to make this positron, which is an anti-electron. And what you'll notice is we have some things that are conserved. So we have +1 charge on each of our hydrogens. So that's +2 on the left side. And then we have a +1 on our new hydrogen, and the positron is also a +1, so +2 on the right. So we have +2 on the left, +2 on the right. The neutron doesn't have any charge. We also have no electrony things on the left, whereas on the right, the neutrino is electrony, it turns out, and the positron is anti-electrony, so that cancels out as well, 0 and 0. We have 2 nucleons on the left, we have 2 nucleons on the right, that's also conserved. So this nuclear reaction actually uses the weak nuclear force, but it releases a lot of energy because as those 2 hydrogens stick together, the total mass actually decreases. It feels weird, but this is what's the binding energy, what it's doing. It's more happy to be helium or to be deuterium than to be normal protium, hydrogen. And so that energy gets released, these particles get shot off going faster than when they came in, and they bump into things, and that's what heat is. Okay, and that positron, I should mention, in reality, it's gonna really quickly run into an electron and just turn poof into energy that way. So its mass also gets converted into energy in this process. Okay, so you might then wonder what happens in the sun. Well, that reaction we just saw is only the first step of many that are going to happen in the sun. And so just like how chemical reactions on Earth often happen kind of one after the other, the same thing happens with nuclear reactions. And so we call this chain of reactions the PP chain, or the proton-proton chain. And you can see what the end result is. The end result is we start with 4 hydrogens, just normal hydrogen. Most hydrogen just is 1 proton. So this is the normal hydrogen. And then those 4 hydrogens go and go and go and go until they turn into 1 helium. And then you can see we've introduced 2 extra hydrogens along the way in this middle step, so we get 2 extra hydrogens out as well. But basically, we're turning hydrogens into heliums, so we're making them happier, and in the process, we're releasing energy. So this is our fuel source. This is how the sun, manages to stay bright for so long. In order to do this, though, it has to get really, really hot. So we have to get how hot? Well, about 12 million Kelvin. Ridiculous, right? Remember, the corona was only about 1 million Kelvin, so we're 10 times hotter. That's the activation energy. That's like you're striking your match and you're putting it to your fire. This is the initial heat needed in order to make these reactions occur. So, okay, what happens in this process? Well, the neutrinos, those are like little ghosts. So as soon as they're made, they just kind of fly away and they don't bump into anything else. So like magic almost. They can just pass through the whole sun, the whole Earth. They can pass through your body, no problem. So we're going to talk more about them later. The photons, those are the little Y symbols, the gammas here. Those are really high energy light, right? Gamma rays are really high energy light. And so what they do is they're going to bounce into other atoms, get emitted and absorbed, right? All the different things that can happen to light. And eventually they're going to get converted into visible light. And that's what we see. We're seeing these photons eventually escape. Okay. How much energy is created in this PP chain? Well, if we had 1 kilogram of hydrogen, so not much, 2.2 pounds of hydrogen, and we were able to fully fuse it with the PP chain, then we would be able to power 17,000 homes for a year. So kind of crazy, right? Just a kilogram of hydrogen, not much at all. So how much does the sun use? Well, the sun uses 600 million tons of hydrogen every second. And so in that process, only a small fraction of that mass gets turned into energy. Maybe a few tons of mass gets turned into energy, but that's enough to power the sun. Okay, and I should mention the PP chain is how our star, the sun, works. It turns out in other stars, there are different types of nuclear reactions that become more important. So, because you might wonder, okay, the helium, what happens to it? Well, eventually the helium wants to turn into other elements, and those will turn into iron. So that does happen in our sun. And you can maybe imagine that once the sun has too much iron, we run into some problems, and maybe that's related to how stars die, which we'll talk about in a later chapter. But basically, this first step for our sun is where it gets most of its energy. But for other stars, they might get more energy in later steps, and we'll learn more about that in the future as well. Okay, so if it's such a good source of energy, 1 kilogram of hydrogen, which is very cheap and abundant, can somehow make enough power for 17,000 homes per year. You might wonder, why is that not what we do for power on Earth? And we're trying really hard. So many of my colleagues work in fusion, and it's a big industry, but it's a very challenging technology. So humans have been working on this problem for over 70 years now, and we've had some successes, but not as many as we've hoped for. So what's the big problem? Well, there are a few. So one problem is that, right, in order to make things undergo fusion, you need to get them really, really hot. How hot? Well, like we just saw, like tens of millions of degrees. That's so hot that it would melt any container you put it in. So how do we do this? Well, we have to get it really hot, and then we have to hold it in place with magnetic fields so that it doesn't touch anything. Okay, so that's what's happening in this picture. This purple inner part, this donut, is the plasma that we're trying to fuse. And you can see that this donut shape allows it to move around in a circle without touching anything, and it's being held in place with magnets. It's kind of crazy. Now, one place where we don't need to worry about confining the plasma is if you're using this fusion method to make a weapon. And so, of course, humans love to make weapons, and modern atomic bombs actually use this to be even more powerful. So you may have heard of a hydrogen bomb. Basically, what you do is you use a regular uranium or plutonium bomb to make the initial activation energy, and then you direct that energy onto some hydrogen, and that causes it to undergo fusion. And it can only do it for a fraction of a second before it destroys itself. But in that fraction of a second of fusion, E equals mc squared, it releases enough energy that it makes your atomic bomb like 100 times more powerful. Okay, so hooray. Yeah, good for everyone on Earth if we have much more powerful nuclear weapons. Okay, so the second problem is that you need a ton of energy input. So in order to make a fusion power plant, you basically need another power plant just to get it started. But once you get it started, you could theoretically, make a lot of energy, make more than you put in, right? Just like how a fire, you need a match to start it, but once you get it going, it can keep itself running. So we have to use some fancy combinations of magnetic fields or lasers or other things to get it started. That's quite challenging on its own. However, like I said, we've made a lot of progress. So the first fusion nuclear reactor is currently being designed by a few different companies and organizations. And hopefully in the next 10 or 20 years, we'll start to see fusion as a viable source of power here on Earth. So the same way we get power from the sun, we can just have a miniature sun down here. Okay, so on that note, we should talk about what details we can say about the sun and how we relate those to its source of energy. So for one, the sun is a plasma. How do we know this? Well, we can look at its spectrum, right? When we ionize something, it changes its spectral lines. So we see the sun's spectral lines. It's very clearly made out of ionized gas. That's what a plasma is. We can also measure its temperature using the black body spectrum, right? And what we see is that it's hot enough that, since it's made of things like hydrogen and helium, we can take those materials on Earth and heat them up, and we see they turn into a plasma. So these little balls, actually, they do contain real plasma. Kind of crazy. You can just buy them as toys. And so when you look in there, this little, web-shaped structure, those are little plasma tendrils. And so, plasmas, they tend to emit some light as they're heated up. Those ions are bouncing around, recombining. They tend to light up. And so the situations where you see plasma on Earth, these are things like lightning, like neon signs. Technically, fire is sort of a plasma. This is a very big debate in the scientific community. There's not a good answer. It's right on the edge, basically. So when you have a plasma, what happens? Well, the hotter you get it, the more things bump into each other. That's also true of gases. Plasmas are different because since they have charge, like positive and negative charges, they can push against each other from farther distances. They don't need to bounce into each other like a gas to create pressure. You can also get forces over longer distances. And so the sun, especially the core, is so hot, it has a really high pressure. And this is important for starting those nuclear fusion reactions. So we can create plasma on Earth and study it here. This is the beauty of astrophysics, right? Is that we can study things on Earth and apply our knowledge to space. But studying plasma is hard. It requires, like we saw, a lot of equipment and energy and knowledge. Okay, so in addition to the sun being made of plasma, we also know the sun is stable. So as a species, we've looked at the sun for a long time. We can also see its effects in the geological record on Earth, for example. And so we can tell that the sun, it hasn't expanded, it hasn't contracted, it stayed a stable size on any time scale that we can measure, basically. So it turns out for billions of years. And so how does this happen? Well, that means that we have to have some balance of forces, right? If you imagine if the sun was pushing out more than it was pulling in, then it would be getting bigger. And if it was pulling in more than it was pushing out, then it would be getting smaller. It would be contracting. So how does this happen? Well, gravity is always pulling it inward. That's the gravitational collapse. But let's think about this carefully. As gravity pulls the sun in and in and in on itself, the sun is big enough that that pressure heats the plasma or heats the gas that then turns into a plasma to the point where nuclear reactions can occur. Once those start occurring, they're like explosions. They're blasting outward. They're creating a pressure that supports the star. So that's how it counterbalances. Okay. So you might wonder then what happens when the sun's energy runs out? Well, when it's converted things into some nuclei that aren't able to fuse anymore, then that pressure goes away. Now gravity starts pulling on it. Okay. What if its energy production becomes more efficient? Well, now it's going to start expanding. Okay. It turns out the sun's future has a little bit of both. So like I said, we'll learn more about the death of stars in a coming chapter. But we call this process, this balance, hydrostatic equilibrium. So hydrostatic equilibrium is where the pressure from fusion and the gravity from its weight balance each other, and you get a stable star. Okay, we also observe the sun is not cooling down. So similarly, we can use Earth's geological record among other clues, and we can see that the sun, not only is it not cooling down, it's actually in its future going to start gradually warming up a little bit. You can kind of see in this chart. Now, I've purposefully cut this chart off. So the 9 billion years is not the end of the line, but it's just the end of what I want to spoil for you so far. So the sun it's very stable, not just in size, but also in energy output. And so if you remember, this is how we argue that the source of the sun's energy can't just be from burning or from gravitational collapse. We need the nuclear reactions in order to allow for this sustained lifespan that we can see in this chart. So the sun's about 4.5 billion years old. It has about another 4.5 billion years before anything interesting starts happening. So it's got plenty of hydrogen and helium to continue to fuse for the foreseeable future. Okay, and so when we start to look within the sun, we know that the energy, the fusion process can only happen in the core. And so we want to think carefully about how the heat goes from the core to us eventually. And it turns out there are only 3 ways for heat to move, roughly speaking. Those are conduction, convection, and radiation. So conduction is like when you touch a hot pan on a stove and it burns you. You need physical contact between things. Now, in a plasma, that means you need particles to be bouncing into each other. And in a star, that doesn't work very well to actually move energy from the inside outward. So conduction, you can basically ignore it. It feels weird, but it's going to be very minimally important inside the structure of a star. Convection is like in your oven or in your home, or how weather works. Basically, you heat something up, it rises, and then it gets away from the heat source, it cools, and it falls back down. So you get these convection loops, these flow loops. In large stars, giant stars, that's really, really important. In our sun, it still is interesting and relevant, but only in this outer layer. And I think we talked about it in the last chapter, this convection zone, which is about the outer 25% radius of the body of the sun. The rest of the sun, the inner 75%, is all dominated by radiation. So basically, in that inner region, convection doesn't work very well. It's just really, really hot. And so the only way for the energy to escape is basically the light, the photons, taking it away. So this is the same way that you feel warmer if you stand in front of one of those sort of infrared light bulbs or something. That's just blasting you with photons that are carrying the energy to you. Now, it turns out that's also how the energy gets from the surface of the sun to us on Earth. So the distance in between the sun and Earth is a vacuum, pretty much. So the only way for the heat to travel is as light, as photons. Okay, so if we actually zoom into that radiative region, though, we find that it's a lot more interesting than you might imagine. So we've already talked about how from the surface of the sun to Earth, it takes light about 8 minutes to travel. Okay. Now, that distance is really large. It's much larger than the radius of the sun itself. So the radius of the sun is only about 2 light seconds. So if the light produced in the core was able to freely travel, it would only take it about 2 seconds to get to the surface. However, the sun is under immense pressure. It's a very dense ball of plasma. And so basically those photons are constantly bouncing into other particles. They're getting absorbed, they're getting re-emitted, they're getting reflected. All this stuff is happening to them. And if you do the math carefully, we say that these photons take a random walk because they're kind of bouncing back and forth randomly. It turns out that it takes light over 100,000 years to escape the sun. So imagine that. It should take it, imagine like your drive to work should take 2 seconds, and instead it takes 100,000 years. That's a pretty incredible difference, but that's what it looks like if you're a photon trying to escape the sun. Now, it turns out that neutrinos are going at almost the speed of light, and so they can escape the sun in about 2 seconds, which is pretty incredible, and we can use them, if we're able to measure them, which is hard to do, to analyze the stellar interior. Okay, so now putting it all together, we can start to actually build a mathematical model of a star. So what does that look like? Well, if we want sort of the simplest possible model that's still useful, which is what we do in physics, then we only need 4 equations. So one equation is mass continuity. So if any material moves around, it can't just disappear. It can turn into energy, but only in the core in a very special way. We also need hydrostatic equilibrium. So whatever inward gravitational force we have has to be balanced by pressure if we want our star to be stable. We need energy generation. So we need an equation that tells us how those nuclear reactions make energy. And we need some energy transport equations that tell us how that energy moves through our star. So if we solve those equations, one type of solution to these is known as a polytrope. And so a polytrope is really nice. It relates the density of the material at a certain place to the pressure. And you only need one parameter, one number, to determine what type of star you have. So by changing that one number, you can describe our sun, or you can describe giant stars, or you can describe a bunch of other things that we're going to learn about later in the course. Of course, this is a really simplified model. It's still pretty useful, but if we want to understand the irregularities, the dynamics, the sunspots, all these sorts of things, flares, we have to do a lot more work. It gets a lot trickier. Those things rely on magnetic fields, so we need to do what's known as magnetohydrodynamics, which is a whole mouthful and is a quite challenging set of equations into itself. So, okay, to wrap up the chapter then, we should talk a little bit about how we know what's happening in the center of, or the interior of the sun. So not only can we determine what's happening just by sort of indirect clues, like by looking at what we observe in terms of the energy and the spectrum and so on, but actually we can use a tool very similar to what we do here on Earth. So on Earth, remember, the way that we see inside the Earth is by using earthquakes. As the earthquake passes through our planet, if it encounters a different layer, so for example, between the crust and the mantle, it'll be reflected or refracted, right? Bent or bounced, depending on the angle it hits, and we can actually see this. So similarly, it turns out there are actually waves, sort of sunquakes, if you will, within our star. And so we call the field of study of these helioseismology. And the way that we can observe them is with the Doppler effect. So we can measure the motion of each little piece of the sun. And what we found is that these different pieces, shown in this diagram here, they pulse. They kind of go back and forth. And they pulse on average at about a rate of 5 minutes. But like every 5 minutes, they'll go back and forth. But we can actually sometimes see a wave develop and spread across the surface. And as this wave, it doesn't just spread across the surface, it also passes through the sun. And we can use that to understand the different layers, the dynamics, the interior, in a way that would otherwise be impossible. Okay, so that's one method to see inside the sun. The other method is using those pesky little neutrinos. So these ghost-like particles, these neutrinos, are produced by the fusion reactions occurring in the sun's core. And they, neutrinos, if you know one thing about them, or if you are to learn one thing about them, it's that they don't interact very much. So even though the neutrinos take away about 3% of the sun's energy, so there are tons of them hitting us, you can see here there are roughly 35 million billion of them that pass through every square meter. So about that many pass through your body every second if you're standing on Earth, which is already far from the sun. So they're quite spread out at that point. But the chances of one interacting with you, maybe one interacts with you in your whole life. Okay, so they're very, very ghostly. They just pass through things. And so what that means is that they get through the sun and they carry valuable information about what's happening in the core. But it also means they're really, really hard to detect on Earth. So you see, it's a blessing and a curse that they don't interact much. In addition, I want to tell you one more property, which is that neutrinos oscillate. So what do I mean by that? Well, we have this picture here. So if you remember, in the sun, in order for the nuclear reactions to be balanced, they have to make the electron type of neutrino. But basically, as neutrinos travel, they are a weird sort of quantum particle. They're going to transform into their other flavors. So each flavor of neutrino secretly has the others inside, and they can kind of transform back and forth as they move. And this is affected by the material they're passing through. So this is one way we were able to actually understand a little bit more about the interior of the sun. Now, okay, I've mentioned how hard these are to detect. So how do we detect them? This is what's really cool. So basically, you need to take a big cave deep underground and put a huge device inside of it to somehow detect these neutrinos. Now, the first way this was done was using basically a bunch of cleaning fluid, like a bunch of bleach, basically, that had chlorine atoms in it. And when the neutrinos, every once in a while, a neutrino would hit one of these chlorine atoms and turn it into an argon atom. And so the scientists had to filter out all this material looking for 1 or 2 argon atoms out of this huge volume. And those corresponded to neutrinos interacting with this material. So it was a really magnificent experiment. Current experiments mostly use water, also sometimes ice. And you can see one here for an example, which is Super Kamiokande. And as you can see, it's built underneath a mountain, Mount Akeno. You do that basically so that we can block all those other particles. We don't want the solar wind or cosmic rays, all these other particles to cause us problems. The neutrinos can pass through that whole mountain, no problem, but everything else gets blocked. Okay, so then within this cave underneath the mountain, you can see it's so large you could fit the Statue of Liberty comfortably inside the cave. And we fill the entire thing with water. So this upper right picture, that little speck on the bottom is a boat with 2 people in it. And all of these little golden spheres are light detectors. So we fill the entire volume with water. And if a neutrino hits one of these water molecules, which very, very rarely happens, right? But it does happen occasionally, it makes a tiny flash of light. So basically, deep in a cave under a mountain in Japan, there's a completely dark tank of water waiting for ghostly particles to every so often hit into the water, make a flash, and tell us about the center of the sun. Kind of crazy. We also have one of these things in Antarctica called Ice Cube, that instead of using water, it uses the ice of Antarctica itself as the detector, which is also really incredible. So it uses like a cubic kilometer, I want to say, of ice to do that. And so you might notice I sound pretty passionate about this. So just to finish up our lecture here, I wanted to tell you about very briefly about my research. So I actually study neutrinos, not ones coming from the sun, but I study what would happen if we had a secret type of neutrino that the others could oscillate into. So not only would they be oscillating into each other, but they might also oscillate into a secret new one that we haven't seen yet that we would call a sterile neutrino. And if, depending on how this happens, we might create a bunch of extra secret particles that could explain this extra mass that we measure in the universe, which we call dark matter. So we're going to learn more about that in the last week of the class. I'll tell you some more about what I do in particular. But we're going to leave it here for today, and I'll see you next time where we're going to start talking more about how we can study the stars.